Homework 31, page 508, section 8.3, numbers 5 through 29 odd and 35, and yes, I put a star here by 35 because it's difficult. Actually, it may be difficult, it may not. You can make it very difficult on yourself. Though, if you just follow the instructions, it shouldn't be too bad. But I'm just going to say, since it's really difficult, and I'm not going to talk about how to do it, you'll be graded on effort for this one. Okay? But it's really not that hard if you just figure it out. Isn't that how every problem is? Anyway, okay. So last time, I wrote something that wasn't exactly true. I said if you have a function, then it could be written in this form. And what I had done was written it as negative infinity to infinity. It's actually not true. Now, if you remember what I said, that this thing can be written like this, this is kind of the real deal, what's going on. All of these C's are, complex numbers, so every Cn is actually some an plus ibn, like that. And there's a way, I'm not going to write all the e's, but if I were to write this out, we'd have C0 and then the e thing, and then plus C1 and the e thing, and so on and so forth. We'd also have all the negatives. You'd have C negative 1 and the e to the stuff, c to the negative 2, e to the stuff. And what you do to turn it from this form to this form, it's not exactly what I'm doing here, but you combine these in a special way so that you get your C0 e to the stuff, C1 e to the stuff, plus the C negative 1 e to the stuff, plus, and then you rewrite, you have your C2 e to the stuff, C negative 2 is C negative 2 e to the stuff, and so on and so forth. And you do some magic, I don't want to get into this, and then you could rewrite this in the form A0, A1, cosine stuff, B1, cosine or sine stuff, and so on and so forth. But the thing is, in order to change its form, you end up taking all the negatives and combining them with all the positives. So this should run from 0 up to infinity. So that's what I did was wrong. I said this runs from negative infinity to infinity. It actually runs from 0 to infinity. And the thing is about this is that if f is a complex valued function, so that is, you have your outputs have a real part and an imaginary part. In other words, if this is some real function plus I times some other real function, right? Just like any complex number you could write as a real part and an imaginary part, where that's a real number, that's a real number. Well, if it's a complex valued function, you have a real part that's a function and an imaginary part that's a function. If it has a complex part, then what you really have here, you don't have the equality here, you have that this is the real part of the f, your original f. In other words, it's just this part right here. But in the case that your function, and this is kind of what we were talking about to begin with, we weren't talking about complex valued functions. I say you take any real valued function, and if that's the case, where there's no imaginary part, where your real part is the function itself, then yes, this thing turns out to just be f of x, and then these things are equal. So it had been so long since I'd seen it. I knew this one in my heart, right? I knew that this was true, and I remembered, oh yeah, and then there's a way to do this. I forgot that the way to go from here to here is to combine all of those, and then you just have running from 0 to infinity. And that's pretty important if you go to actually calculate one of these things. So if your function is real valued, and I just want to say one more thing. Let's imagine here that we actually wrote out this sum if n is 0, then plugging in a 0 right here gives you a cosine 0, which is just 1. And so you have your a0 cosine 0 plus b0 sine. Well, plugging in your 0 gives you a 0 right there. Sine 0 is 0. So this is just a0 times 1, right? And then plus all the other terms. a1 cosine blah, blah, blah. Plus b2 sine, or b1 sine blah, blah, blah. Plus a2 cosine stuff. Plus b2 sine blah, 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 blah. This thing is always just, this part always just gives you a0 as a constant. And so in practice, it's easier to rewrite this as just the a0 plus the sum as n now goes from 1 up to infinity of the a(n's) cosine n pi over lx plus bn sine n pi over lx, like that. Why am I bothering with any of this, especially if we're not going to do it? Well, if you just went along and did from the last lecture and tried one of these by yourself, you'd find what often happens is, let's say you find your formula for your bn's, right? Which is you take your original function f of x and you integrate that against sine n pi l over x dx, and you do some work and you end up with the formula. What often happens is that this formula has an n somewhere in the denominator. So maybe you do some work and you find it's negative 2 pi over n pi blah blah blah, or negative 2 over n pi. That's your bn right there. And you could see that if you just plugged it into here and then you just take your formula, plug it in like that into Desmos. Desmos is going to say at division by 0. I'm not graphing that for you because you just plugged it in. So what you end up doing is remembering. It's kind of like when you have your ax squared plus bx plus c equals 0. You could just use the formula and that's fine. But if your a happens to be 0, your formula, x equals negative b plus or minus blah, 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 over 2a, you wouldn't do that in the first place. You wouldn't just plug in a 0 if your a were 0. It's kind of like the same thing here. It's like, in the 0 case, this is always 1. That's always 0. So you don't bother plugging in an n equals 0. It's easier to just do it like this. Plug it into there. That way, if you do have an n in the denominator, in this term right here, you're plugging in a 1 and you don't have any problems. So, I just wanted to say that. I messed up. I'm sorry. Okay? Forgive me. I'm not perfect. Anyway, so yeah, and just one more time. If f is a real function, then it can be written like this. As long as f isn't really exotic, right? So, okay, moving on. Let's compute the integral. Squared dx. Pause the video and attempt this guy. You might think, okay, I know this, right? This is arcsine. Arcsine x plus some constant. So maybe this has something to do with that. You might think, oh, since that's 1 over that, this is 1 over arcsine. And you're absolutely wrong if you try that. Because let's just take the derivative of this. This is the same thing as arcsine stuff to the negative 1. Let's use capital F here. And so if you take the derivative of it, you get negative arcsine negative 2 times the derivative of arcsine, which is this thing. Clearly not the same thing as this right there. So, right, integrals don't work that way. You can't say, oh, well, if that's that, and that's that, then this must be 1 over that. No, integrals don't work that way. So, what you do is you say, I'm going to do a u substitution on this. And you say, I'm going to let u equal 1 minus x squared. so that du is negative 2x dx. Okay, so then dx is negative du over 2x, and so you get, okay, subbing this in, I get u, then dx is negative, bringing the negative out there, du over 2x, so negative 1/2 root u du over, oh, I don't want an x down there. So I'm going to have to solve here, bring that over, bring that guy over. Take the square root, and hopefully it's positive, I guess, right? Probably. We'll take the positive one, because depending on where you are, you're probably positive, whatever, who cares? Because this isn't gonna do us any good. I guess then what? Did I go any further on this? Yeah, no, it's just making your life more complicated. I mean, maybe you multiply the top and the bottom by root u. Multiplying the top by root u gives you u. Root u in the bottom gives you this. I guess that's u over root u minus u squared. That seems to have made my life even harder. Boy, I don't know. Yikes. What do we do? This does not look like a viable way of going from there. So, what do we do with something like this? Well, it's the topic for today. It's called trigonometric substitution. Many students say that this is the most difficult topic in integral calculus. I think, personally, the reason why that is because of the way that the book teaches it. I have a way of doing it that I think, and this is me, that I think is much easier. And hopefully, my hope is that by teaching you my method of doing this, it will not be as complicated or as difficult as it is if you just did the book's way of doing it. Okay? So, here we go. Without further ado, this is what I do. I have an integral with a root and something squared in the root. So what I'm going to do is think, well, this is very much like a triangle. We could realize this as the side of a triangle, in particular, a right triangle. And in that case, if it's, and we'll get into this a little bit more, if there's a minus sign there, then it's got to be this one or this one, right? And we'll see that in just a second. So I'm going to let this thing, the root with the stuff in it, be one of the sides. And it does not matter which side. This is another thing that I don't like about the book. The book wants you to do it a specific way. It does not matter which way you do it. And we'll see that in a minute, okay? So I'm going to let this be theta. Now that forces these other two to be something specific. And if you square that and add it to this, you could think, like you have, this is some length. And what we have is like, we're going to square these. It's going to have to be that c squared is equal to a squared plus whatever this stuff is, squared, 1 minus x squared. Of course, you could fill this in with anything you want, but usually with the minus there, you want that to cancel this thing here. And so if we let a be x, then life gets really easy. So that's usually what you do, is if you have a minus in here, you let this side be one of them, and then whatever the minus that stuff is, not squared, is what you put right there. And then that's nice because this just works out to 1. If c squared is equal to 1, then c must equal to 1. C must be equal to 1. There you go. Okay? Okay. Now what we're going to do is just a bunch of calculus. And so the way that I set this up, what I'm going to want is something equals x. Okay? Some trig function, this is trigonometric substitution. Some trig function of theta equals x. Well, it would be, the easiest one would be x over 1, so I guess that would be sine, opposite over hypotenuse. So sine theta equals x. Okay? Now, thinking about what we have here now. What we're going to do, what we want to do, is substitute each of these parts. Here's one part, here's another part. Now I want them in terms of trig functions. So I'm going to need a dx, so that means I need to take the derivative of this. So I take the derivative of sine, I get cosine theta, d theta. It's just like doing a u substitution here. Okay, it's the same idea. Only we're just choosing our substitution to be something that helps us out. Okay? So now dx is going to get replaced by that. Now I need to figure out how to express this part, the integrand, in terms of sine function, or sine function, in terms of trig functions. And I have a triangle here, so I'm going to use that. I'm going to think, how do I get this? How do I get this by itself? 1 minus x squared. Well, in terms of trig functions, I'm thinking, well, here's 1. This over 1 is the thing itself. That's what I want. That's the part that I want. What trig function gives that to me? Because that would be adjacent over hypotenuse, which would be, in this case, cosine theta. Okay? So now we have all the parts of our integral. I have 1 minus x squared is equal to cosine theta. Okay, so I'm just going to replace that. There's that. That's just cosine theta. dx is cosine theta d theta. So cosine theta d theta. Now I've substituted theta for x. Okay? And this is actually quite easy to do. This is the same as cosine squared theta d theta. Boop, boop. Which is the same thing as 1/2 plus 1/2 cosine 2 theta d theta. Okay, now we could actually do the integral. That should work out to 1/2 theta plus 1/2. Now let's think about the antiderivative of cosine. It would have to have been sine of the same stuff. So it would have to have been sine 2 theta, but I'm going to need to bring down a 2. So 1/2 like that. Of course, plus a constant. Now let's clean this up a little bit. So I'm going to get rid of this stuff and give me some space here. Okay, so let's clean this up. Here's 1/2 theta. 1/2 and a half is a quarter. A quarter sine 2 theta. And this is where I think doing it the book's way really gives people a hard time. I'm not going to tell you what the book's way is yet. I'm just going to do it my way and say, okay, well, if sine theta equals x, then theta is equal to arc sine x. So I'm going to replace that theta with arc sine x. Interesting that it does involve arc sine, but it's not just arc sine or 1 over arc sine, but he does show up there. That's kind of cool. Now, plus 1/4 sine 2 theta. Now here's where we're going to have to use a trig identity here. And sine 2 theta has nothing, 2 theta has nothing to do with this triangle. You could try to figure out what these would be if you extended this. Here's 1 theta. Maybe you add on another theta and then do some kind of crazy geometric stuff. Yikes. Or you could remember your trig identities and say, can I rewrite sine 2 theta as something? Yeah, then this is one you're going to want to remember too. Sine 2 theta is the same thing as 2 sine theta cosine theta. So I'm going to replace sine 2 theta with this right here. So that's 2 sine theta cosine theta. Guys, please try to keep it down. Thank you. Okay, we're almost there. we need to get everything back in terms of x. We're halfway there. Now the 2 and the 4, I guess we have 1/2 sine theta, cosine theta. And this is why I like my method here. We have sine theta and cosine theta. We also have the triangle, which relates theta and the x's. And so sine theta is just opposite over hypotenuse. So sine theta is just x. It's also written right there. Okay, so that's nice. Arc sine x plus 1/2. Sine theta is just x. Cosine theta is adjacent over hypotenuse. So it would be just this right here, plus a constant. And now, there we go. There's your answer. Take the derivative of it, and you'll get that guy right there. So how does the book say to do this? Well, the book's method says that if your integral involves something that looks like this, right? Root of something squared minus x squared. Then use the substitution x equals a sine theta. If it's this with the plus, you use x equals a tan theta. If it's this with the x first and the x squared first and then the minus, to use x equals a secant theta. Okay? Now, the problem with this, and we'll just do it. We'll just do what the book says to do. Okay? So if we're going to do, I guess in this case, a 1 minus x squared says to do x equals 1 times sine theta. Okay. Knowing that I'm about to substitute, I need a dx, so I take dx of both sides. I get cosine theta d theta. Cool. And now I just substitute it in directly. And I say, okay, 1 minus sine x squared dx. Oh, sorry, that should have been sine theta. Dx is now cosine theta d theta. 1 minus sine squared is cosine squared. And so I take the root of both sides, I should just have cosine. So this is just cosine theta, cosine theta. And so far, it looks like the book's method is pretty cool, right? Well, let's remember what I did, right? We square that and we do a half plus a half cosine 2 theta. And you end up with, this is 1/2 theta plus 1/2 sine 2 theta plus a constant. And now, you tell me, you look at this stuff right here, and tell me, how do I get back in terms of x? Well, I mean, I guess what we do here is sine theta, so that's arc sine x equals theta. And so then this is, of course, like what we got before. This is 1/2 arc sine, blah, 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 blah. But now we have sine of 2 arc sine x. What is that? How does that get you back to the answer with, you see, like right here, this is what I think is the real hard part. Like, my way is conceptually difficult because you have to, you'll see it's going to get a little bit more difficult, but you have to construct a triangle and find all the bits and stuff like that. But then at the end, when you go to substitute your stuff back in, your answer's all right there on the triangle, right? Like any trig function you want, if this is 1 minus x squared and this is x and that's 1, any trig function involving theta, you could get that in the original expressions. Here, now you have to figure out what is sine of 2 arc sine x. I don't even want to think about that. Like, I mean, I guess technically you could say I'm done, but what is that? That doesn't help. You can't check that. I mean, I guess you could check it. And there are ways, but then you have to memorize a bunch of identities involving arc sine and arc cos and stuff like that, and it's just a huge pain. So I like my way. I think my way is a little bit better. Number 6 from your book is the definite integral from 1 up to 2. The square root of x squared minus 1 over x. Okay, so I'm looking at this and I'm thinking, okay, I have a square root with x squared in it minus something. Okay, I'm gonna try a trig substitution. And so in order to do that, I'm gonna need a triangle. There's theta, it's a right triangle. Now, I could, knowing, so there's a minus in there, and so I know that I need to let this x be one of, let the root be one of these things. And as opposed to your book, which says to always do it a certain way, it doesn't matter which way. We're gonna do it both ways, and I'll show you. But anyway, I'm just gonna choose this one right here, x squared minus 1. Okay, so when I square that out, this thing needs to cancel that thing, so that should be 1. Then whatever's positive in here should be this thing there. And let's just check that. 1 squared plus that stuff squared should be the same thing as that thing squared, right? 1 base squared plus the other base squared equals the hypotenuse squared. Is that true? Yes, it's true. Okay, cool. So we got the correct triangle. Now, it's going to be easiest if I get x equals some trig function. What's that going to be? Well, I'm looking at these guys here, and so it looks, what goes through my mind is, well, cosine theta is 1 over x. So 1 over that, x is 1 over cosine theta, and so x is equal to secant theta. Now in this case, I happen to get the same substitution that the book says. If you go back a second ago, the book told me that if I have it in the form root x squared minus a squared, then I do x equals a secant theta. The a is 1, so I'm doing what the book tells me to do. You'll see it doesn't matter if I use that or something else. But at any rate, this is where I am so far. Now I'm going to need a dx. Okay, so dx is when I take the derivative of secant theta, I should get secant tangent. I'm going to check myself. D theta. Don't forget your d theta. Is that right? Does that come out to, yes, secant tangent. Okay, cool. All right, and so now I'm going to do my substitution and say, what I'm going to do, the way that I think about this is I'm going to break the integrand up into different parts. I have this thing, which is this, and that's the same thing as times that, right? I'm just kind of pulling this thing apart so that I can think about, okay, how do I write this part as a trig function? Well, that's that one over that one, right? That one over that one would be tan, I guess. So tan theta is root x squared minus 1 over 1. And so there's the tan theta. Times, okay, how do I get 1 over x in terms of trig functions? I guess that over that would be cosine, right? Cosine theta is 1 over x, which is what that part is. So cosine theta. dx, we already found out, is secant tangent. So secant tangent d theta. Now, okay. Looks really bad, but cosine and secant. Always, when you get to this point, always check and see if something cancels out. And indeed, right, secant is 1 over cosine. So cosine times it will cancel out. Tangent times tangent is tan squared. Tan squared theta d theta. Now, okay, hold up. Tan squared. And nothing's really coming to mind. I can't think of, nothing in the top of my head that makes me think of tangent. So maybe, or tangent squared. So maybe I'm going to do something like this. I can't remember the identity, but I know that there's an identity that involves tangent squared. How do I get tangent? I guess it's sine squared over cosine. So I'm going to do this, cosine squared. Cosine squared, that's 1, plus tan squared. equals secant squared. So this is tan squared is secant squared minus 1. Maybe I'll have more luck if I change it. I don't know. But I do know secant squared, that's the derivative of some function. So I'm thinking this might actually work out to my benefit. So here we go. Tangent squared is secant squared minus 1. Okay. That's actually easy, because the derivative of tangent is secant squared. So that's why I chose to go down this route instead of trying to do some kind of substitution or something like that. I knew that tangent squared and secant squared are related, and I know the antiderivative of secant squared is just tangent. Nice. Okay, so there's tan theta. The antiderivative of 1 is theta, and so minus theta plus a constant. Okay. Now here's where you might think, uh-oh, we took a wrong turn somewhere. Because you're like, oh, theta, there's theta, x is secant theta. Uh-oh. How do I, uh-oh. Well, we could just say arc secant x is equal to theta. Hold up. It won't be too bad. Trust me on this, okay? Now, tan theta, on the other hand, well, that's easy because you have your triangle right here. You don't have to try to get it, and if you just did this, like the book said, good luck. I don't know what you do from there, but what I'd probably do is make a triangle. Anyway, you already have your triangle. Tan theta is opposite over adjacent. So tan theta is just root stuff over 1, or just root stuff. There you go. Minus theta is arc secant, whatever that means. It's just the inverse of secant, plus a constant. And actually this plus a constant stuff we don't really care about because it's a definite integral, right? So we're going to evaluate this guy up at 2 and down at 1. So, okay, I'm going to get rid of most of this stuff here to do that. All right, here we go. So, I'm going to plug in a 2, minus off, plugging in a 1. Plugging in a 2 gives me root 4 minus 1 minus arc secant 2. Plugging in a 1 gives me 1 minus 1 in there, so that's a 0, minus arc secant 1. And now you're like, what is arc secant 2 and arc secant 1? I guess, technically we're done. But let's actually figure this out. Because we want to check this in the back of our book, and it certainly does not look like this. So that's a minus minus, I'll go plus arc secant 1. Okay, alright, so let me get rid of this. Let's actually compute what this is. Oh, that shouldn't be arc, that should have been an arc secant. So whenever I do arc anything of something, the first thing I do is say, well, hold up, there's some angle theta which is equal to this, right? Because you have some trig function, you plug in an angle theta and you get out some value. And so when you arc trig that function, whichever one it is, you get back your original angle. So I'm going to say arc secant of 2 is some angle theta. What angle? Well, that means that angle theta, I'm thinking arc secant is just 1 over sine. I'm sorry, 1 over cosine, right? So you plug in some value into 1 over cosine, and I'm thinking, okay, you have adjacent and hypotenuse here. And secant theta would be hypotenuse over adjacent. And if that gives you a 2, right? That's what this says, right? You take secant of this secant of that, and you get out a 2, then hypotenuse over adjacent must be 2. Or I could think about it like this. Hypotenuse must be 2, adjacent must be 1, and now, and you can see, I think you know which triangle this is. This should be root 3. I've drawn it a little funky. It should look more like this. There's 1, 2, root 3. This should be pi over 3. Pi over 3, right there. So that should be that guy. Okay? Another way you could think about it is, well, hold up. Arc secant, it's the same as if I flipped this. Arc secant 2 equals theta is the same thing as my arc cos being whatever that is flipped, right? However you want to choose to think about that, that should be the same thing right there, right? Because if cosine theta is adjacent over hypotenuse, then secant theta is hypotenuse over adjacent. And so, right, and this is for the same theta, so you take arc cos of both sides, like this one, arc cos adjacent over hypotenuse. Do that over here. The same theta should give you that arc secant hypotenuse over adjacent. And so what I'm saying then, if those are equal to each other, then arc secant of hypotenuse over adjacent is the same thing as arc cos adjacent over hypotenuse. Right? So if you have that in your head, you could just say, oh, this is the same thing as arc cos of 1 over whatever that is. And arc cos 1/2, that's an easy one to do. And is what you do it with the same triangle. Boom. Okay? So arc secant of 2 then works out to, this is pi over 3. And we add now arc secant 1. Okay, so arc secant 1 is the same thing as arc cos 1 over 1, right? Yeah? And so arc cos of 1, you plug something into cosine, got out a 1, I guess it must have been a 0. Right? I guess the angle must have been 0. Right? There's cosine. You plug in a 1, you get out a 0 into arc cosine. Similarly, here's cosine. You're like, where in this interval do I get an output of 1? Well, I guess when theta is equal to 0. And so arc secant of 1 is 0. And finally, we get that this integral should be root 3 minus pi over 3. I'm going to put that up here. Root 3 minus pi over 3. And is that what I got? Let's make sure. Yes, it is. Okay. Now, let me go back, because I said I was going to do this. I said it does not matter how you set up your triangle. The book is very adamant that you have to set it up a certain way. And I say it doesn't matter. I said you could set this up, you could put that anywhere. Well, not anywhere, I guess. If it has a minus in it, it has to go here or here. Right? But now, this guy changes that way. Or, oh, wait, nope, 1. Be careful with that, right? Now let's double check that I've set this up the right way. Square that. Add it to that squared. Do you get, yeah, okay, that should work. You can check that at home if you want. Okay? So now I need x by itself. I need some trig function equals x. And I can see that one over that one. Sine is 1 over x. So I want, I guess, 1 over that. So cosecant theta equals x. I need a dx, so I take the derivative of cosecant, and I get negative cosecant cotangent. Yikes. That negative always messes you up, right? Now we need to break this up and say, okay, this is the same thing as this. Break it into pieces. Now, how do I get, I guess it's that over that, I guess cotangent theta is that over that. Yeah? Now the 1 over x, I guess would be sine theta gives me my 1 over x. And so I do all my substitutions. I get, this is cotan. 1 over x is sine. Dx is negative. I'm going to pull that negative all the way out in the front. And I get cosecant cotan d theta. Again, the sines and the cosecants cancel, and I get this is equal to negative cotan squared. And we could do the same thing, right? The way I chose to do this was cotan squared plus 1 is cosecant squared. So again, cotan would be cosecant minus, so negative cosecant squared minus 1 for the same reasoning is that I know cosecant squared has an easy antiderivative, and it's negative, right? Don't forget that negative. This turns out to be negative cotan theta minus theta. Yeah? Bringing that negative in here. Now I'm going to get rid of all this stuff to give me some room here. Okay? Here's that. I do want to keep my cosecant theta equals x. Okay. Distribute the negative in, and we get cotan theta minus theta plus a constant, but it's a definite integral, so I don't care. Cotan is, well, tangent's that over that, so cotan is that over that. So x squared minus 1 minus theta. Cosecant theta is x, so theta equals arc cosecant x, which is the same thing as arc sine 1 over x, right? By the same reasoning that I used before, right? Arc cosecant is the same. If x over 1 is cosecant, then 1 over x is sine. Oh yeah, okay, well that's easy enough. So minus theta is the same thing as minus arc sine 1 over x. Hopefully you're not evaluating that guy at 0. And we're not. And there's another thing. I'm not going to be a stickler about this, but we do need to check and make sure. Like, if you get to the end and you go and you end up plugging in something like this, arc sine of 7, like, let's say we're integrating from 3 to 7. It's like, no, you're not. Well, in this case, it's fine because you have 1 over that. But you see what I'm saying? Right? Like, if you end up with an arc sine of something that's out of the domain, something went wrong. Probably not going to happen with these ones. Just like this. I didn't think anything about that until we get to here. Now I'm seeing I plug in a 1 and a 2. I'm not going to have any problems here. And so, let's just do that. I'm going to plug in my 2, evaluate it, plug in my 1, evaluate it. Plugging in my 2 gives me root 3, just like we saw before, minus arc sine of 1 over 2. Okay. Plug in my 1, that guy is a 0, and now I have minus arc sine 1 over 1. Okay. Arc sine of 1/2.
Whoa, that's not
1 over 2, 3. This is pi over 6.
Oh, sure.
So arc sine 1/2 is pi over 6. Root 3 minus pi over 6. Minus minus is plus. Arc sine 1. Arc sine of 1, where does sine give me a 1 as an output? This is the first time it does. Right here at pi over 2. So that must be pi over 2. Root 3 minus pi over... Oh, well, look at what I did. That was supposed to be pi over 6. Minus arc sine 1/2 is pi over 6. Minus pi over 6. Plus arc sine 1 is plus pi over 2. And you can see pi over 2 minus pi over 6 is indeed minus pi over 3. So it doesn't matter which one you do, right? If everything works, it doesn't matter how you put these up. You don't need to have your x be x times a secant theta. It's going to work out, okay? It's just that in the end, your answer might look a little different. Cotan theta minus theta. And if this weren't a definite integral, you might end up with some stuff. You might do a bunch of stuff and you find, oh, it's equal to x plus arc sine x. You have some you have some indefinite integral of something. F of x dx. And you get as your answer after a lot of work that it's equal to this right here. And then you go and check in the back of the book and it tells you that it's this. And you think, oh man, I did something wrong. Well, no you didn't. Because remember that this is arc sine. But then the integral of -1 over this is arc cos. So yeah, it's and then it's off with the constants and stuff like that. But so this type of thing might happen. And I think one of the reasons that books do this and say, always, always, always use this as your substitution. You have to use this as your substitution. It's just so that when you check in the back of the book, you get the same thing and it's not off like that. I don't know why they do it the way that they do it. I don't like it. And then you have to memorize like 3 things. You have to say, if it's this, if it's x minus this, then it's secant. If it's this minus x, then we use sine. And if it's this plus this, we use tangent. And then you have to, those are the 3 things you have to remember. Or you could just remember, I have a root of something squared, let me make a triangle. And then it doesn't matter which triangle you make, everything's going to work out. Your answer might look a little different. It might look like this. But they're equivalent. So, chill out. I like my way. If you like you go with the book's way. You go ahead and do it. If you like it, roll with it. I prefer my way. Number 10 is the indefinite integral of t to the 5th over the square root of t squared plus 2 dt. Pause the video and figure out the triangle that we're going to use to substitute here. Okay, so I see a square root and something squared inside of it. And so I'm thinking, okay, trig sub, I'm going to try that. So I'm going to make a right triangle here. Here's my theta. It's a right triangle. And so, okay, with a plus there, the only possibility is that this thing shows up here. Why is that? Well, with a plus, right? I mean, just think about you have A, B, and C, and the relationship here, the Pythagorean theorem gives us that. So the only way that you can have a plus, right, if you're jockeying these three things around, is if it's here. Otherwise, you either have c minus a or minus b equals the other stuff. And then when you take the square root, right, you end up with a minus there. The only way that you could have a plus in the square root with a triangle is if that square root is indeed the hypotenuse itself. So it's forced to be there. Now we have a choice of what we want to where we want the other ones to go. And I chose to put the t here. And now it's not going to be a 2 there, right? It's got to be the square root of 2. It's got to be the square root. Because if it were like t squared plus a squared, obviously the a goes there. And so you gotta keep that in mind. Like if it's not something squared, you do have to take the square root. Okay? All right, now we need a trig function that just involves t, because we need to get a dt somehow. We can't get it just a t, but we could get close. I could say tan theta equals t over root 2, right? Opposite over adjacent. Now it's not too hard to get the t by itself, right? I could say, oh, then t is just root 2 tan theta. And we end up getting the very substitution that the book told us to do. So if we weren't doing Justin's method, and we just did what the book said, we would do this right here. And then you could just go through and just substitute everywhere that you see a t, and you'd have root 2 tan theta to the 5th over root 2 tan squared. I guess that would be 2 tan squared theta plus 2. And good luck, right? Looks like, I mean, we'd have to pull out a root 2 out of that, so that we'd have tan squared plus 1, which is secant squared. So that's root 2 secant squared, square root. So that's root 2 secant in the bottom. Root 2 secant down here. T to the 5th up there. Okay, so root 2 can come out. Root 2 to the 5th, tan to the 5th, over 1 secant. Okay, have fun. That's going to get ugly. What we're going to end up with is going to be ugly too, but it'll be ugly in a different way. It's just, this is how the book says to do it. And of course, then you're left struggling, looking just at this at the end when you have sines and cosines and a bunch of stuff pops out. Good luck. Again, that's not how I like to do it. I'm going to split this guy up. I'm going to rewrite him as, let's just keep the t to the 5th by himself. I'm going to do this guy right here. And dt. Oh, we haven't got our dt yet. Okay, sorry. So, take the derivative of this. Tangent goes to secant squared. So that's root 2 secant squared theta d theta. Don't forget your d theta. Derivative of t is just dt. There we go. Okay, now t to the 5th. And this could mess you up a little bit, but we already have this right here. So again, like I said, ours is going to get ugly too, but if we raise that to the 5th power, and again, like what I would probably do is look at this and say, okay, I need the t by itself. That's a constant, so I'll be able to do it, and so I would have, okay, tan theta is my t over root 2. 5th, raise both sides of the 5th power, do some stuff, and yeah. Anyway, or you could just look right here and say, okay, then t to the 5th is the same thing as all of this to the 5th, root 2 tan. Okay. Oh, let's get the other part. 1 over that. 1 over that. Well, I can't get 1 over that, but I can see that cosine theta, I need that guy in the denominator. And the most straightforward way of doing it. Here's the thing, I don't want to use sine. because then we're bringing in a variable that I don't want to mess with. Right? We could just say sine, and then, I mean, I could have broken this up this way, t to the fourth, and then said t over this right here, t squared plus 2. In fact, let's do both of them. In this case, it gives us this. In this case, I'm looking at cosine. Oops. Cosine theta is the root 2 over this stuff, t squared plus 2. And so why am I doing, oh, I was doing it because of that right there. And so 1 over root 2 cosine theta is 1 over t squared plus 2. And so that's what I substitute in here. So t to the 5th gives me root 2 tan to the 5th. And then this works out to 1 over root 2 cosine. 1 over root 2 cosine. Then my dt is that stuff, and that's what I do. Over here it would be a little bit different. I would have t to the 4th, so it would be tan, root 2 tan to the 4th. Root 2 tan to the 4th. And then this would be, like we said, sine. That's just plain old sine theta is t over t squared plus 2. T over t squared plus 2 is sine theta. Nice. There's my sine theta. dt is that stuff, and I plug it in. You could go either way, and that's yeah, either way is going to get you ultimately to the same place. One looks a little nicer than the other. I kind of like this because I don't have that weird root 2 in there. But we could just continue on here. I'm going to do it this way. I'm just going to go ahead and do it that way. Okay? So we're not done. We need the dt. The dt was this stuff. So root 2 secant squared theta d theta. Okay, so let's just double check here. We had t to the 4th was that right there. T over that, I just chose that because it's nice. I mean, I can see, oh, sine gives me that, and so it's just sine. That's easy. I like that. There's no weird root 2's floating around there, so I do that. It gives me that. There's my sine theta. The dt is all of that stuff. Root 2 secant squared d theta. Now let's see if some stuff cancels out. In fact, I'm going to write this up here. Root 2 tan theta, all raised to the 4th power. Sine theta, root 2, secant squared theta, d theta. Okay, so that was all of that. I'm going to get rid of this and this. Get rid of this, and let's work. Okay. So now, root 2 to the 4th. That's the same thing. There's 4 of them. 1, 2, 3, 4. 2 of them gives me 2. 2 of them gives me another 2. So that's 4. That works out to 4 tan to the 4th theta sine theta root 2 secant squared d theta. Okay. 4 and root 2 I'm going to pull out as 4 root 2. Now, I'll go ahead and write it up. What we're left with is tan 4 theta sine theta secant squared d theta. What I do, now remember our last class, I said don't worry about all the tangents and stuff like that. We're only going to worry about sines and cosines. The reason why is because at this point, like if you spend a whole lot of time worrying about, oh, how do I deal with tangent and how do I deal with secant and blah, 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 blah. You're just wasting a bunch of time because you can just turn this into sines and cosines. Right? You can take every trig function and just write it in terms of sines and cosines. So let's do that. Okay? We have 4 root 2. Tangent to the 4th is the same thing as sine to the 4th over cosine to the 4th. This is sine. Secant is 1 over cosine, so secant squared is 1 over cosine squared. That's a lot easier. My 4 root 2 comes along for the ride. Integral. Now I have a total of 5 sines on the top. So sine to the 5th theta. Over 6 cosines on the bottom. Theta. D theta. Is that what I got down here? Make sure I got this right. Yes. Yeah, that's how I do it. Okay, now, do we have an odd power? Yeah, we do. So let's pull an odd man out. And I'm going to say, okay, 4 root 2. In the top, that's the same thing as sine to the 4th. Sine d theta over cosine to the 6th. Okay, this might get a little ugly. I'm going to go ahead and, so I have the one guy by himself. That's the one guy by himself. So I want to get everybody else in terms of the other one. So I need to get sine in terms of cosine. So 4 root 2. I could rewrite sine to the 4th as sine squared squared. But sine squared is 1 minus cosine squared. Squared. So let's do that. 1 minus cosine squared theta squared. We have our 1 sine left over. And on the bottom, we have 6 cosines. D theta. Now let's do a U substitution. I'm going to give myself some room. I'm going to erase this stuff right here. Give myself some room for a U substitution. And I'm going to let U equal the stuff that I have the most of, cosine. So that du is negative sine theta d theta. D theta works out to negative du over sine. That negative du, or you can look at it like this, there's that, we'll replace that with a du, however you like to do it. We're going to pull that negative out front, so now he's negative 4 root 2. That guy's gone and he's just du. This is now 1 minus u squared, quantity squared, all over u to the 6th. Now I think it's going to be easiest, since that's just squared right there, let's just multiply it out. Probably be a lot easier on us if we just do that. So, it's the same thing as negative 4 root 2. Squaring out the top gives us 1 minus 2u squared plus u to the 4th. There's a du floating around. Okay, and that's all over u to the 6th. So I could rewrite that as over u to the 6th, over u to the 6th, over u to the 6th. Why am I doing that? Well, because breaking it up into individual terms usually makes life a lot easier. So this is the same thing as u to the negative 6. Minus 2, let's see, 2 on the top, 4, or 6 on the bottom leaves 4 on the bottom, so that's u to the minus 4. 4 on the top, 6 on the bottom leaves 2 on the bottom, so that's the same thing as plus u to the negative 2. There we go. Now, this is the same thing as negative 4 root 2 times, okay, we have to make the power bigger, so he's going to be u to the minus 5 over the minus 5. Got to make that bigger, so he goes to minus 3, u to the minus 3. Need to bring that minus 3 into the bottom. 2 stays put, 3 goes down. It's minus, a minus minus makes that positive. It's got to make that bigger, so he's got to be e to the negative 1. But he's negative, right? Divide by the negative 1 makes that negative. There we go. Negative 1 right there, plus a constant. Okay. I'm going to rewrite that up here and get rid of all this work here. Okay, so minus 4 root 2 times minus 1/5 u. And I'm going to write it like this. Minus 1 over 5 u to the 5th plus 2 over 3 u to the 3rd minus 1 over u, like that. But u, oh, I erased him. Oh, that's dangerous. I erased what my u substitution was. Do you remember what it was? Really dangerous. You don't want to do that. We let u equal cosine theta, didn't we? Okay? So now, substituting him back in for root 2, we have negative 1 over 5 cosine to the 5th plus 2 over 3 cosine cubed minus 1 over cosine plus a constant. Okay, well, there's a nice thing about having this right here is this takes the guesswork out of what cosine is. Because if you did what the book said, you'd have this. And you'd go, okay, cosine now. Yeah, so I'm just going to look right here and say, okay, well, cosine theta is the same thing as root 2 over root t squared plus 2. Okay, now each one of those is in the denominator. So that's the same thing as flipping the fraction. I mean, I could have written this all as secants, really. I could have said minus 1 over 5 secant to the 5th plus 2/3 secant cubed minus secant. And then so then secant theta is just 1 over that. There's my t squared plus 2 over root 2. And then I could just replace each of those, however you want to think about it, right? I like to think about it as you plug that in at the bottom, take him to the 5th power, and then he like flips up. Whatever. Minus 4 root 2. So I'm going to write that as negative 1/5, and then flip that guy and make him to the 5th power. So that's root t squared plus 2 to the 5th over root 2 to the 5th plus 2/3 that stuff to the 3rd over that stuff to the 3rd. Bottom's that. This is root t squared plus 2 minus, now it's just 1 over cosine, which is this. Now technically we're done, oh, plus a constant. Technically we're done, but I happen to notice that we could get some cool cancellations going on here, right? Especially each one of those is going to have a root 2 left over. So root 2 to the 5th, that's 5 of them. That's 2. 2 of them is another 2, so that's 4 times root 2. Well, that's kind of nice, right? That 4 and that root 2. So I'm just going to rewrite this. This is the same thing as 4 root 2. If it were 3 of them, that's the same thing as 2 root 2. So I'm going to rewrite this as 2 root 2. And then we just have a root 2 there. Okay. So now the negative stuff comes in. That makes that a, oh, the 4 root 2 cancels the 4 root 2. And and the negative makes that positive, so all I'm left with is that right there. Just a minute, buddy. Negative comes in, makes that negative. Root 2 kills that root 2. This 2 kills that 2. And so we're left with 4/3 make sure I haven't messed that up. Yep, 4/3. And then we have this to the third. Now that comes in, negative makes that positive. Root 2 kills the root 2, and we're just left with a 4. Root t squared plus 2, finally plus a constant. And is that what I got? Yep, minus 4/3, that stuff, 4, that stuff plus c. And when I did this yesterday and checked it in Wolfram Alpha, every one of these that I'm going to brag here, every one of these that I did, I got right the first time. That never happens. I'm just, something crazy happened yesterday. Because you could see there was about 1,000 places where you could have messed something up, right? And yeah, sorry is another reason, one of the many reasons why this is one of the hardest things you're going to do this year, okay? Like, this is just, it's rough. And wait until the next example, man. Oh man, it's really rough. But anyway, so this is the idea, right? A few different ways I could have written this stuff that it could have looked different. Like if I just kept this cosine down here, each one of these would have been like minus 1, 5, and then it would have been root 2 over the root stuff to the 5th. And maybe my final answer looks like that. I look in the back of the book and it looks like this. Well, do a little bit more work and make this look like that, okay? If you cannot get your stuff to look like what the book says, then at least, like, do try to make your stuff look like this. And if it doesn't, and you've done everything you can, check it with Wolfram Alpha, right? Take your final bit, take the derivative of this stuff, and it should come out to look like that. Failing that, you say integrate and put this stuff in it, and it might spit out what your stuff looks like, maybe not. It's usually not. As you can see, this stuff gets highly variable. But so there you go. So if we want to summarize my method here, it's basically, if you have an integral with something like this, a squared minus x squared, the square root of a squared minus x squared, then you construct a triangle that's like this, right? You have this thing on, and it could be on either one. You have the root either on this leg or this leg of the triangle, doesn't matter which one. And then you have, notice you have something that's positive under the root and something that's negative under the root. The positive thing ends up on the hypotenuse. Okay? Here, we have a root of something squared minus something squared. I'm going to construct a triangle again where the root goes on either one of these, doesn't matter which one, and then the positive thing that's in the root goes on the hypotenuse. Okay? If we have the square root of something squared plus something squared, then that's the positive thing that goes in the root, right? We talked about that a minute ago. And then you got these guys as your legs. And again, they could go either way you want to do it, does not matter. Now, this is where it gets a little bit tricky. Is when you have something like this. And this could be a plus or a minus, and if it's a minus, then these same things apply. But I'm just going to choose a case where it's plus. One thing you could do is just rewrite this as a sum of squares, right? Where you have the square root of ax all squared, and then you have the square root of bx squared. And now you're just back in this right here, where you say, okay, well, it's plus, so this thing goes here, and then each one of these goes in a leg. And again, you can see I did it differently this way than that way. The x ended up here, the x ends up here. Does not matter. You can flip those legs, it's all the same. Another thing you could do, and you might want to do, depends, is to say, let's factor an a out of here. Could factor an a out of this. That puts an a in the denominator down here. Which is then, I could rewrite that as root a gets pulled out. This guy is x squared. Plus, and then again, I want to write that as one thing squared. And so instead of b over a, I could write that as root b over a squared. And that's the same thing. And so like if that shows up in your integral, well, nice thing about this is that if that shows up in your integral, you could pull that out and then just forget about that root a until the very end, right? And so you don't have to deal with this guy down here. And from there, now you're dealing with this, forgetting about that root a, and you could get something like this. Root theta. It's a plus, so this guy has to go here. There's my x squared and my root b over a squared. And then each one of those is just some leg. We can make this my x and make this my root b over a. Either way, it's a little bit cleaner, but ultimately it is equivalent, however you want to do it. This just, does that a little bit better. Or it makes it gets rid of a little bit of an a, I guess, but he still shows up down here, so it's not like it's completely gone. Although I think this is a little bit easier to deal with. Then you can forget about him until the very end. Just bring him in at the end. Whatever, whichever way you prefer. That's how you want to deal with these. But this is basic this is like a summary of my method. All right, the last example, number 26. And this one is a doozy. This one is really rough, okay? We got the indefinite integral of x squared over 3 plus 4x minus 4x squared raised to the power of 3 halves, okay? If you're just looking at that, you're thinking, that's not what we're dealing with, roots and stuff. Well, 3 halves, right? That's the same thing as this right there, right? And that is where I like to start. I like to have it written like this. It's written in your book as to the 3 halves. My first step is if I see something to the power of I don't care over 2, I'm going to rewrite that like this. Now I'm looking at this, and it's like, well, that everything we've been dealing with so far has been where you have some number squared plus or minus some variable squared, and that's not what that is. So one thing you might think to do right away is, oh, I see a polynomial, I see a cubic, so I'm going to try to factor it. And let's just see, it looks like it might factor if you have a 3 and a 1, right? And I'm doing this a little bit differently than we normally do it, right? But maybe a 2x on both of these, something like that. Let's just try it and see. First, outer, inner, last. First gives me the 3. Outer, 6, inner, 2. Can we get a 4 out of that? Yeah, if we do plus 6x minus 2x's. And then that gives me my minus 4x squared. Cool, okay, it factors, nice. So then this works out to something like this. Cubed. Oh boy, now what? I don't know, we split it up like this, minus maybe? 1 plus 2x. Cube it, so maybe you cube each of these. But now, that's still in the denominator. Uh-oh, like that's not looking very helpful at all. So what do we do? Well, the goal is to try to turn this thing, right? Because of what we know is that if I have something squared plus or minus something squared, now I have a method of dealing with this type of thing in my integral. It doesn't matter where it is either, right? It could be under something, it could be over something, doesn't matter, I have a method. And it might bear fruit, right? So I'm thinking, how do I turn this thing into something squared plus or minus something squared? And if you recall, right, what we just talked about was, doesn't necessarily need to be something squared, plus something squared per se, because you could rewrite that as something squared, right? Where we do like this type of thing. So if I could get this as just something with x squared plus some other stuff, then I have a way of going forward. What I'm going to do is rewrite this thing like this with the method, or in the order that I'm familiar with. And I'm going to think, okay, so what I'm trying to do is rearrange this thing so that maybe we end up with something squared plus something. Can we do that? Any methods? Is there any method that maybe I stressed and stressed and stressed to memorize because it'll come back? It'll come back to you in ways that you might not think. So you want to be able to do this in your sleep. I give you like 1,000 of these to work on. Yep, completing the square is what we're going to do. So if you remember, to complete the square, we take this expression and we factor this number out of these two terms. So I'm going to factor out a negative 4. That leaves me with an x squared here. And if you remember, I said the first thing you want to do is write it like this, right? Give yourself some space, right? So factoring out a negative 4 from here leaves me with a negative x. So that's a negative 1 right there. We take half of that and we add it and subtract it squared. So half of that is 1/2. And we add and subtract squared. Why? Because that makes a perfect square right there. That thing right there itself is a square, a polynomial squared. And it's x, that sign is minus, so we do a minus there. And then whatever that is what this is. And it's squared. And I'm just going to double check that part right there. First, outer, inner, last. First gives me x squared. Outer gives me minus 1/2 x. Inner gives me minus 1/2 x. The last gives me plus 1/4. And I'm going to check that that's that. That's x squared minus 1x plus 1/4 is 1/2 squared. So yes, that's that. I haven't changed it because I added it and subtracted it in place. And so I'm going to rewrite that as minus 1/4 right there, plus 3. We're almost there. I'm going to continue. I'm going to distribute this guy in. And so we have minus 4x minus 1/2 squared. Minus minus makes a plus. 4 divided by 4 is a 1. I can drop the parentheses. Plus 3 gives me this plus 4. 4, but that's all under a square root, and so it's not the form I'm looking for, right? What I'm looking for is this right here. Now this happens to be nice because there's a 4 and a 4. This could have been really ugly, right? We could have ended up with something like 7 minus 3 and then something squared. But that's no problem, right? Like we could rearrange that if we wanted to. I could, I don't know, pull out the 3 and say that's the same thing as 7/3 minus the thing squared. Like that. And then pull out that root 3. So that we have 7/3 minus whatever the thing is squared. And then we could say, oh, but that's the same thing as root that stuff squared. And so then in my integral, I could just forget about that root 3, right? Pull them all the way out. And so same kind of thing here. It just happens that that 4 is nice when you pull him out. That he gives you 4. What's left over? A 1 minus the stuff. Like that. That's really nice because now we could split him up into 2 roots. And so we get the square root of 4 is 2. this guy works out to something actually not too bad, and we could deal with him. But it's still going to get ugly. It's still going to get really ugly. So, what I've just found is, and just to be clear here, right? This is the same thing as 3 plus 4x minus 4x squared. But that thing is the same as this. Yeah? Now, just like to take a minute. Remember when I said, when we first did completing the square, said that the book has you do it a certain way where you do it as an equation, and they tell you to subtract off the c so that this gives you that, and then you factor out and you do all that stuff there. I said we are not going to do it that way. We're going to do it in place. Because if you learn it this way, you've learned it as something you do to an equation, right? And I've had so many students say, I don't know what, like, we're in this situation. I say, oh, the answer is, the first thing you want to do is complete the square. And they say, but I don't have an equation. Because they think that completing the square is something you do to an equation. It's not what you do to an equation. You could do it in place. And that's why I stressed that we want to, and it's weird because there's this step where you add and subtract the same thing, and it's weird that you're adding 0, but we rewrote 0 in a way that helps us. And I said it's really important that you learn it this way, because that way, when you look at something like this, you could go, man, if I could just turn that into something squared, and I can, and I don't need an equation to do it. This isn't something you do to an equation, it's something you could do in place. And so we could do this in place, right here, and rewrite this thing as that thing, and that's going to help us out. Okay, so let's do that. We just said that the root of this stuff is equal to this stuff. So I'm going to rewrite my integral with that in place of the other things. So but be careful, because that cube in the denominator, we need to take care of him too. Okay, so I'm going to do that right there first. Then I'm going to replace that root with this right here. 2 root 1 minus that stuff. 1 minus x minus a half quantity squared dx, which is the same thing as x squared. Now that's 2 cubed times the root cubed. 2 cubed is 8. So that's an 8. And then the root 1 minus x minus a half squared cubed. So that 8 I can pull out as a 1/8 times the stuff like that. So to save some room, I'm going to rewrite this one without that 2, pulling him out as an 8. So that's the same thing as pulling the 8 out if the 2 weren't there. Okay. All right. Okay. Now what do we do? Well, I see an integral. In the integral, I see a root, and it's something minus something squared. But that's something squared. So I could, if I wanted to, I could go ahead and write my triangle. But what I think I want to do is do a u substitution right here to make this a little bit simpler. Okay, so I'm going to say let u equal that stuff right there, x minus a half. Which is nice, because when I do du, it's just dx. There's no crazy stuff to do. I am going to have to rewrite my x in terms of u. But that's easy. This works out to u plus a half is equal to x. And that's not going to be too bad, because he's just squared. We could square that out, no problem. So 1/8 integral. The x squared is now 1 plus a half squared, or u plus a half squared. In the denominator, we have some stuff cubed, but that denominator is pretty simple now, 1 minus u squared. Now let's do a triangle. Why? Because I see that I have a root of something minus something squared. That tells me I could do a trig sub here. So, I can do this any way I want. The root needs to, because it's a minus, the root needs to be one of these. I'm going to go ahead and do it like this. The positive thing in the root, its square root needs to be here. The negative thing, its square root needs to be here. I'm going to double check it. Square that, 1 minus u squared, plus that squared.
No!
Is that equal to 1 squared? Yes, 1 equals 1 squared. Okay, so we're good. Now, I need to get, oh, there's a dx here, or ooh, a du. As you can tell, we're going to get to the end and we're going to have to substitute back in what u is, or we're going to have to substitute our thetas back in for u's, and then we'll have to substitute our u's back in for x's. So it's going to be nice to have this all written out. So, I need a u. I want just something equal to u. What trig function gives me just u? Well, sine theta should do it. Sine theta gives me u over 1, okay? I need a du, so I need to take a d theta. Take the derivative, we get cosine theta, d theta equals du. Now, how do I do this? Well, the u in that, how do I want to do this? Because u plus a half, ugh, that's kind of yucky.
Fine.
But what I can do is go ahead and split this up in the top. Or, I'm sorry, multiply this out in the top. That might help. So I'm going to go, okay, 1/8. The integral of first outer inner last gives me u squared plus 1/2 u plus 1/2 u, so a total of plus 1 u plus a quarter. Okay, so that's plus u plus a quarter all over root 1 minus u squared cubed. Okay, now well, we could just go ahead and just do the signs and stuff like that. But I think what I want to do with this is split this up into 3 integrals. And this is going to work for every single one of them. Okay? So let's go ahead and split him up into 3 integrals. We have 1/8 times the integral of the u squared over cube root 1 minus u squared plus the integral of u over cube 1 minus u squared. Finally, now that's just a quarter, right? Like I could pull, I'm going to pull him out just to begin with. There's a quarter, so now it's just 1 over cubed 1 minus u squared. Running out of room here, but you see the idea, all right? I just rewrote this guy as that guy. Okay, so we have 1/8 times a bunch of stuff. Now, this thing I'm going to split up as the integral of u squared times 1 over that stuff cubed. Now, cosine theta, so I just see that cosine theta is equal to this thing right here. Right? So I could just replace this with cosine theta. U squared, well u is u over 1, so that would be sine, and it's right there, right? So u squared is the same thing as sine squared. This is 1 over stuff cubed. What's the stuff? That's just cosine. Oh, sine squared over cosine cubed. That's not bad. So give it a second. So sine squared theta over cosine cubed theta, but now, and what I didn't write here was the d thetas. D theta, or these are all du's, sorry, du. Each one of these has a du in it, and du is cosine theta. So each one of these du's needs a cosine theta d theta. So cosine theta d theta. Okay. The next one, same trick. The bottom's the same. That's still just cosine cubed. U is just sine. So we have u becomes sine theta. And the bottom, root 1 minus u is just cosine, so that's cosine cubed. Same thing, cosine cubed theta. Now times cosine theta d theta. Plus, I pulled out the quarter. 1/4. 1 over, that should just be cosine cubed. Cosine cubed theta. What's on the top? The du becomes cosine theta d theta. Whoa. Alright. Still have my substitutions written down because I'm going to need them in a minute. Now, let's see if we can cancel some stuff out. One cosine on the top cancels one of them on the bottom, so this is just sine squared over cosine squared. So that is the integral of sine squared over cosine squared is tangent squared. Okay, now this is where we need to be a little bit creative, okay? This cancels down to sine over cosine squared. Now, if we wanted to, we could rewrite the bottom in terms of sines, I guess. Or let's just think of what else this is. This is the same thing as sine over cosine times 1 over cosine. Sine over cosine is tangent. 1 over cosine is secant. And is that the derivative of some function that we know? Yes, the derivative of secant is tangent times secant. So this looks like the direction I want to go with this one. So I'm going to rewrite this one as tangent secant. Pays to have a lot of this stuff in there. Plus 1/4 cosine over cosine cubed is 1 over cosine squared, which is secant squared. Is that one that we know? Yeah, we know the derivative of tangent is secant squared. So this reduces to secant squared. So that's the way I want to write it, because I know it's antiderivative fairly easily. Okay, so 1/8 times. Now, we did this one earlier. This worked out to be, I'm not going to go through it because we actually did it. We change that to secant squared minus 1, right? Take the antiderivative of it, and we get tangent theta minus theta. Tan theta minus theta. Tangent secant, like I said, just is secant. 1/4 secant squared, it should be tangent. Right? Yep, so 1/4 tangent. Plus a constant. Now, here we go. These are not so bad. Theta, the theta is going to be arc sine. Wait, whoa. Yes, yeah. Theta gives me arc sine u is theta. Tangent is u over 1 over u. Okay, so this is 1/8. Tangent of theta is u over root 1 minus u squared. Minus theta is arc sine u. Plus secant. Secant is 1 over 1 minus u squared. Plus 1/4 tangent is u over root 1 minus u squared, plus a constant. We have 1/4 of these plus 1 of those. Those are 5/4 of those. And bring that back up here. That's 1/8. And we can also see that there. 1/4 tangent plus 1 tangent is 5/4 tangent, which is the same thing as 5/4 of this. So that's 5u over 4 root 1 minus u squared. Minus arc sine u plus 1 over root 1 minus squared. But we don't plus a constant. But we don't care about u. We care about the x's. And here u was x minus a half. So I'm just going to replace every one of those with x minus a half. And hopefully I end up with the same thing that I got earlier. 5x minus a half. Parentheses are your best friend here. 5 root 1 minus x minus a half squared minus arc sine x minus a half plus 1 over root 1 minus x minus a half squared. It's all multiplied by an eighth plus a constant. And that should be, let me double check here. Let's see. 5/4, 4, 1, and that. Yes. That stuff there. Minus plus a constant. And believe it or not, I checked it in Wolfram Alpha.